this video, I'm going to use the well-known algorithm for solving a linear system that involves augmented matrices. The algorithm is, I'll give you an overview of the algorithm. It's to take a linear system, there's the linear system, we take a linear system, then we write the augmented matrix corresponding to that linear system, where we take the coefficients and we put them into the augmented matrix. Then we use row operations, I'll tell you what those are in a second, to reduce the matrix to something called reduced row echelon form. Reduced row echelon form, briefly, has leading ones that staircase down, and whenever there's a leading one, there's zeros elsewhere in the column. Okay, so we want to achieve reduced row echelon form by using row operations. Then once we have reduced row echelon form of the augmented matrix, then we can go back to the land of equations and we'll yield a new linear system that will be equivalent to the original linear system insofar as it will have the same solutions as the original linear system. Okay, so without further ado, let's create the augmented matrix, okay? Okay, so the row operations that we can use which yield an equivalent linear system are as follows. We can interchange two rows. We can multiply any row by a non-zero scalar, or we could add or subtract a multiple of one row to or from another, right? I noticed that I'm using the word row because we're no longer in the land of equations, we're in the land of matrices, so we refer to these entries, in terms of their row and column. Okay, all right, so let's see, what can we do? I want to get a leading one here, so I have a leading one here, and I want to eliminate the 2 and the negative 1, so I get zeros elsewhere in the column. Well, to do so, I can take row 2 minus 2 row 1s. Let's leave row 1 intact, okay? And then row 2 minus 2 row 1s. This gives me a 0. Negative 10 minus 2 negative 6s gives me a 2, right? Because negative 10 minus 2 negative 6s is negative 10 plus 12, and negative 9 minus 2 negative 4s is negative 9 plus 8, so that gives me a negative 1, and negative 4 minus 2 negative 5s is negative 4 plus 10, which gives me a 6. All right. Similarly, what we'll do to get rid of the negative 1 here is I'll add 1 row 1 to row 3. So again, row 1 stays intact. We add 1 to negative 1, of course, we get a 0. Negative 6 to 6, we get a 0. Oh, that's nice. Okay, this matrix is reducing nicely already. And negative 4 to 5 gives us a 1. And then negative 5 added to 3 gives me a negative 2. All right, so the next step is to get a 1 here, but notice that I already have a leading 1 in row 3, right? So I think I'll use that leading 1 in row 3 to knock out the negative 1 and the negative 4 there, okay? So in order to do so, what am I going to do? Row 3 is going to stay intact, all right? And then I'm going to add row 3 to row 2, just one row 3 to row 2. So that gives me 0, 2, 0, and then negative 2 added to 6 gives me a 4. Now how about I add 4 row 3s to row 1? Okay, let's do that. So 4 zeros added to 1 is 1, 4 zeros added to negative 6 is negative 6, 4 1s added to negative 4 is 0, and then we have 4 negative 2s added to negative 5 is negative 13, correct? Right, because 4 negative 2s is negative 8. Negative 8 added to negative 5 is negative 13. Voila, there we go. All right, how about we get rid of this negative 6 here? I guess I could divide or multiply row 2 by a half. you know, I may as well do that. It doesn't matter. 6 and 1/2 a dozen of the other. So if I divide row 2 by 2, I get a 1 there and I get a 2 here. All right. And then I'm going to add 6 row 2s to row 1. All right. And that will yield our final reduced row echelon form matrix. So row 3 stays intact. Right, we're not doing anything with row 3, but I'm going to add 6 row 2s to row 1, right? So what do I have? 6 zeros to 1 stays a 1. 6 1s added to -6 gives me a 0, which is what I desired here, right? And then 6 zeros added to 0 is 0, and 6 2s added to -13 yields a -1. Okay? All right. So now observe that the coefficient matrix is the identity matrix, thus the augmented matrix is in reduced row echelon form. So I can now go back to the land of equations and inspect my equivalent linear system. All right? So let's see. Well, we have x is equal to -1. We have y is equal to 2. Right? And this may seem a bit silly, right? Because I could have read off x, y, and z. But I want to go back to the land of equations because that is the algorithm. And if you had an augmented matrix that led to you know, infinitely many solutions, like a 1 or 2 parameter family of solutions, you're going to want to go back to the land of equations because it'll be easier to figure out, you know, who is going to be the free variable. So I like to go back to the land of equations. All right, let's see. We have the solution to our linear system. Of course, this solution is very easy by inspection, and that solution is just a single point, right? The solution S is equal to a point in 3-dimensional space, 1, 2, -2. Right, where x is equal to -1, y is equal to 2, and z is equal to -2. So let's check our answer because, you know, what good is it if it doesn't work, right? So we'll substitute those values into each one of the equations, and with any luck we'll see that the left side is equal to the right side. So what do I have? I have -1, and then -6 times 2, that's -12. -4 times -2 is +8, and is that equals to -5? Well, sure, because -13 plus 8 equals -5, and that checks, right? -5 equals -5. Let's look at equation 2. So equation 2, we have 2 times -1, that's -2, minus 10 times 2, so that's 20, and then minus 9 times -2, well, that's +18. And does that equal to -4? -2 minus 20 is -22, plus 18 is indeed equal to -4. Beautiful. Okay, finally, let's look at the third equation. We have -1, that's a 1, and 6 times 2, that's 12, and 5 times -2 is -10, and does that equal to 3? Indeed it does. 1 plus 12 is 13, minus 10, and 3 equals 3, and it checks. All right, great.